Hello again. Okay, let's wrap this up. Okay, this is what we said earlier on about coming up with a tentative dimension. Tentative means awalan, awal tu. So it's just an estimation. So of course, when you have a situation where you want to build up, retain the height, you know the height. Say you want 10 meters, 12 meters, or 15 meters of ground here. So what we don't know is that if you want a cantilever wall, how far in this is going to be, right? How far, or rather how wide, the B value, right? The breadth of your base of the wall, we don't know that. So normally it's being assumed to be 0.6 to 0.7 H. So if your H, the height is 10 meters, so the B will be like 6 or 7 meters, okay? And a fair bit of it will be in the part where it's being the backfill, okay? Now, for a wall like this, for a cantilever wall like this, what are the dimensions, what are the forces that are acting on it for us to conduct the analysis? Now, first and foremost, we have the weight of the wall itself, right? And secondly, we have the, when I say the weight of the wall, we are talking about W2 and W3, the stem and also the base, okay, got it? And then we move on to the weight of the soil that's sitting on the wall. Now, W4, do you think it's going to contribute to the stability of the wall, or is going to be bad for the wall? You are right, it is adding on to the self-weight of the wall, hence it's going to be good for the stability of it. Alright, then we move on to the soil that is being backfilled at the front of the wall. Obviously, you're going to put some soil here so that can make up the height, and also and this again is sitting on the base of the wall, is going to add on to the stability of it. Alright, that's W1. And next, you have this active pressure, horizontal truss, PA, coming in from the back. You'll probably ask, why is it not horizontal, why is it slanting? You're right, again, because the soil, the backfill soil is not horizontal or flat, it has an angle. So of course then you have Larayan vector, a vertical component, horizontal component, so the combined force is going to be an inclined one, okay? And next, what else do we have? We have a passive pressure coming in from the front. Why? Because you have backfill material at the front. Okay, this is the depth that we are talking about, D here. So is this passive pressure good or bad for the stability of the wall? Pushing it, good, obviously, alright, because it's increasing the resistance of the wall against whatever that's pushing from the back. That's your backfill. Right? And next is the shear force, or the shear resistance at the base of it. So this is totally frictional. And it's why at the base of the wall, we usually pop in a layer of granular material, sand bed and things like that, so that the friction is good, okay? Apart from giving an even surface for the wall to sit on. Last but not least, we are talking about the bearing pressure. So these are from the grounds, okay? And you can see that the shape is always a trapezoid. So the force that's acting, the resultant force will be somewhere around here, correct? This is the combination of a rectangle and a triangle. So the combined force will come somewhere around here, okay? Not in the middle. Okay, and here are the formulas that we can use to calculate this, to conduct the analysis. For the active and passive pressure, we don't need to talk about that anymore because I learned that in chapter 2, right? Using the Rankin's theory or Coulomb's theory, whichever one that you prefer. And for the sliding force, we are talking about, remember, the shear force, the shear resistance at the base of the wall. So we are looking at the friction, really. So in sand, it's totally dependent on the delta. There's a friction angle between the base of the wall and the sand. And normally we take it 0.67 phi. What is phi? It's the angle of shear resistance of your sand, which can be obtained from your shear box test. Very good. And if it's in clay, say the supporting material is clay, which is will be quite unlikely. It will be the SU, the shear strength of the soil, multiplied by the breadth. That's the width of your base. Okay, simple formulas. What about for overturning? Recall, we did say that it's about the resisting moment, MR, over the overturning moment. It should be greater than 1.5. So for the overturning moment is your active thrust, there's a PA, multiplied by 1/3 of the height. That is actually going from the mid-height of your triangle to the base of the foundation, to the base of the wall, right? And for the resisting moment, is all the moments that you have to resist the loads that's coming in from the backfill of the wall. Okay. As for the pressure along the wall, along the base, remember we talked about that, it has to lie within the 2/3 of the base. Here is how it looks like actually. There's an eccentricity, as you can see, this is a bearing pressure coming in, the breadth of the wall is B, middle of it is B/2, eccentricity, remember the resulting force of the Q, that's your bearing pressure, is not acting in the middle because this shape, the bearing pressure diagram is trapezoid. So it's somewhere, wow, maybe like 1/3, right? So going to the centroid of it, it will be E, eccentricity. We learned about that before. And in order to find E, this is a formula. Actually, it's not quite a formula. You could mathematically derive this as we talked about in chapter 2 before. Okay, but if you don't like, you can just memorize this if you like. And the E value they're talking about, the eccentricity, should be less than B/6. Why? Because when it's B/6, then it will be kept between the middle 2/3 of your wall. Okay? And the pressure distribution, in order to plot this chart out, the max is over here, the front of the wall. This is a formula. It must not be more than your allowable bearing capacity. As for the minimum, that's on the other end, that's on the backfill end, it should be greater than 0, obviously. Okay? You see that in terms of analysis, sometimes we look at a wall that has pressure here that's positive, at the back here going up to negative, so that's not acceptable. Alright, the wall is going to fail, meaning that it's going to, simply put, it's going to settle, go right down, because the soil cannot take the weight of the wall, including the backfill material. Okay, hence it got to be greater than 0. Okay. And you note that this bit that we're talking about, B/2 minus M, the moment over the total vertical force, is actually your X. Right? This is no magic. You have seen the details of this in chapter 2 actually. Right? Go back to it and look at it. Yeah. Okay. So a quick example. It's just want you to compare the earth pressure distribution and the active thrust that is developed behind 1. A cantilever retaining wall. 2. A braced excavation. So before we look at braced excavation, let's look at the cantilever wall. We need not draw it out or things like that because it's a simple one. It just says that we want to have the pressure diagram out. The wall height is 5 meters, and at the top of the wall obviously is 0. And what is the pressure at the base of the wall is 0.33. That's a Ka, active coefficient or active earth pressure, multiplied by sigma V. Sigma V we know is the gamma of the soil multiplied by the depth of the soil, 18 times 5. That's the answer you get. So what is the active thrust? Remember, chapter 2 is the area of your pressure diagram. So it's a triangle, so it's a half of the height multiplied by the base, which is 30. So you get 75 kN per meter run. Alright, per meter run because the wall is long. Okay, now let's look at braced excavation. What's a braced excavation? A braced excavation looks like this. Okay, you want to cut it out, and usually it is going to be vertical. Why? Because you are going to put bracing in there. These are the braces. Okay, now if you are having sand in your at your excavator site, then the pressure diagram actually is a rectangle. From the bottom to the base, they are of the same value. And to calculate that, is it 6.65 Ka gamma H? But if it's in clay, be a bit careful. It is a trapezium, and it's H/4 at the top and bottom, and in the middle bit is the remaining half. And what is the value of the lateral earth pressure is 0.2 to 0.4 gamma H. Okay, and this example, it is sand, so that will make our life easier. It's just a rectangular diagram that we are going to use. So from the top to the bottom, because it's rectangle, the formula is the same, 0.65 Ka gamma H, so 18.5. Okay, and what is gamma H? Is sigma V, right? Get that right. Okay, 18 is the gamma of the soil, 5 is the height of the wall. That's 19.5 kN per meter square. And the active thrust that's coming in, because it's rectangular, is just 5 times 19.5. So you get the answer of 97.5. What is the question about? The question asks us to compare between the two, between the cantilever wall and the braced excavation. So the wall of the braced excavation and thrust will resist a force of 97.5. We calculated that. And for the retaining wall, the cantilever retaining wall is 75. So it's actually higher if you use a braced excavation. it does make sense, right? Because of the very vertical cut. And hence the earth pressure at the base of the wall is higher than the one that is for the raised excavation. So it's the other way around. Okay, so that's all for it. You can go through this calculation again. Any questions again, you can PM me or WhatsApp in the group and things like that. That's all for chapter 3. Do go through it and learn well. Stay home, stay safe. Bye bye.